So, welcome to the sixth lecture on causality for AI and ML. So today we will be wrapping up the core causal basics. We will touch on some topics which might be not that important, but in theory, but maybe interesting if you apply stuff in practice, especially if you can't identify some of the causal effects because you don't have collected enough data or have been given enough data. And yeah, we will show some ideas on how to still get estimates or bounds for those estimates to make some or draw some conclusion from the data that we have. Right. Okay, so maybe we start with a short recap on the last lecture, which was this interesting causal graph, whatever you think of it. But the exercise or task was to write down all the independency statements according to the d-separation. And also one thing that we only require the minimal set of conditioning sets, because once you have conditioning sets and don't, yeah, it's like if you then condition on the parents of these variables, you get bigger conditioning sets, but it doesn't change the independencies that you have. Has anyone, given this graph, an idea which independencies we could observe? Has anyone looked at this exercise again? Otherwise, I will just present the answers. So any ideas? Maybe the easiest one are the unconditional independencies that we have. Okay. Then maybe just switch to the solution. At least you can have a look at that afterwards again. So what we see is that if we don't condition on anything, like T and E are unconditional independent, same for T and S, because they are not confounded by anything. And since we don't condition on any variable, like none of the colliders opens the path, then the same holds for T and M and D and E, D and S, given once D and once E. So, I mean, again, this is, I think, what we have somehow seen in the second and maybe third lecture. Just look at the graph, check which variables are independent under which conditions, and for the exam, we will present an exercise sheet later. I think this might be about the difficulty or the complexity of the graphs we will show you. So that's nice. We can read off independency statements from a graph. But the thing is that usually if we have data, we don't know this graph yet. And we might get these independency statements by checking the data, by iteratively going through it and checking all the variables with statistical tests. And from these statements, we want to, again, construct a graph, in the best case, a fully directed graph, or at least a CP-DAG, where we might direct some edges and might need to leave some undefined or undirected. So again, we have the independency statements that we get, in this case, from our data. And we start with a fully connected graph where we draw all the edges. And the next step basically is to remove all the edges according to the independency statements. So we ignore the conditioning sets for now and remove all the edge pairs that we have in the front. So T and E, T and S, T and M, and so on. And what we get now is the skeleton of the graph. And I think last time there was a question, okay, so now how do we direct any of those? So we saw these meek rules, which then help us, okay, if we have some directed edges and directing another edge in some direction would form a cycle, then because of acyclicity, we know it needs to be the other way around. But somehow we need to start with something. And particularly, we want to, in the first step, direct V structures, which in this case are those two. And so I think there was a question why we don't direct maybe these two edges into V structure and so on. And basically recall this rule we had in a slide last time that tells us to direct a V structure, the variable cannot be in the conditioning sets of the two variables. So, for example, for D and S, you might wonder, okay, why don't we direct an additional V structure via E? And this is because in the independency statements or the conditional independencies, we have one test where E is in the conditioning set. And this also goes for all the other pairs. So the only V structures left are T, D, and E, and D, M, and S. Yes. Then again, yeah, sadly, I think we might do another example at some point where we have some of the meek rules. But again, these are can be kind of complex depending on the graph. So we have a graph here where we have directed most of the edges. We have this last final edge, at least, I mean, we can check, does directing it in one or the other direction form a cycle? In this case, it does not. Also, none of the other rules are fulfilled. You just have to believe me here. So this is the CP-DAG, which represents the Markov equivalence class. So this is the best we can do from observational data without any other parametric assumptions or something. Okay, are there any questions on that? No, then let's continue with the second question. So I think this might be rather easy to see or to think of. So the idea is we have a causal discovery algorithm, and it discovers some CP-DAG, so maybe this one. And in addition, we are given a causal order. So a causal order is basically a total ordering of variables, which means if one variable comes before another, then at least, or then in a graph or whatever, the earlier variable causes the later variable, at least if they're somehow connected. So basically, what this relates to is that if you have a DAG, it corresponds to a partial order of the variables. So you know, for example, like D comes before M, S comes before M, and so on. But you don't know any ordering of D and between D and S because they are not directly connected. You know, E comes before M, and so on. So given a causal, like a total ordering, things become much easier, right? Because if you're given this list, you actually don't need to apply all these rules, because for every variable in this total causal ordering, you just check, does S come before M in this order? Does T come before D in this order, and so on? So sometimes this is helpful because experts might give you this sort of like ordering because they inferred via some time constraints and so on. And if you're given this order, depends, of course, on the scenario you're in, whether you can have it or not. But then you really just need the skeleton because for every pair of connected variables, you can directly direct them. So this is basically the answer to that. And more specifically, the causal ordering is an even stronger criterion than a DAG, because a DAG only tells you a partial order. So maybe that's an interesting thing to think about.
So the causal order would be linear?
Yes, so the causal order is really just a linear order list or something, which gives you a total, like, yeah, assigns a total index to every variable. Okay, then maybe let's start with some new stuff. And so far, we've been talking about, okay, what are causal graphs? How can we discover them? We have seen several algorithms, but if you're developing new algorithms or if you want to test some assumptions and have a test set and whatever, you might be interested in ways to actually measure if your causal discovery algorithms discover the right thing. So if they are able to discover the right causal graph, because we make a lot of assumptions. So of course we make acyclicity assumptions, sometimes on the presence of noise. So if you have logical systems where like that are deterministic, where there is no noise, some tests might fail. Always, or most of the time, all of these algorithms are proven under infinite data, which basically means, okay, in the sample limit, our independency tests are guaranteed to succeed or like to give the true answer. In reality, we have outliers in the data. We have some weird, like other effects that might lead to these independency tests failing. And of course, like sometimes we just can't observe some of the variables. Then we saw in algorithms, namely FCI, which can kind of deal with that. But still, due to all of these assumptions and whether they might hold or not, we might get a causal graph which is maybe not fully correct in the end. Yeah, and the question now is what can we do to measure the correctness of the graph we recover? So the first idea would be to go and check the accuracy. So basically what you do, you take your causal graph, your DAG, you look at the adjacency matrix, and you just sum up all the, like do that for your true graph that you know, your reference and the predicted one, and you sum up all the correctly predicted edges and normalized by all the possible edges you have. So n squared is the normalization term, and then you check for every correctly or incorrectly directed edge. So does anyone see a problem with that, where this might fail? Okay, so if you remember, we are talking about DAGs. So the thing is that no matter what we do, if we rearrange the variable order or whatever, we get a like strictly upper or lower triangular matrix, which basically means that like independent of what our algorithm discovers, if we get a DAG, at least half of the variables are 0. And even like worse. I mean, we can predict the complete opposite, that would be bad. But a lot of graphs that we deal with are sometimes, or can be assumed to be sparse. And for sparse graphs, we have n squared edges with n variables. But let's assume we have 100 nodes, then we have 10,000 possible edges. And just assume we have a sparse graph with only 500 edges and an algorithm which does not predict anything. So it doesn't predict a single edge. Then because we have so many like possible edges which are just not there, these 500 edges that we mispredict like don't influence the accuracy that much. We have still a 95% accuracy, and that might be a problem. Yeah.
I assume that the true positive and false negative, I'm a bit confused about the formula. And why is it divided by the total possible edges?
Yeah, so basically it is, if you look at the adjacency matrix or whatever, so it's the so true positive and true negative in this case is true positives are the edges that are correctly predicted, and true negatives are the absent edges that are correctly predicted. So the ones that are not there, and we are correct about it.
Oh, okay.
Yeah. And the normalizing, like then if you think of the adjacency matrix, right, the normalizing term is that we like look at every single cell of this adjacency matrix and normalize by that. So yeah, of course, like this might be okay to use if we know we have dense graphs, but still it's not the best thing to do, or you at least need to be careful with that. So what is more often used is precision and recall. So we only look at the edges that we have in our true graph. Yeah, so that's recall, exactly. And precision is from the edges we predict how many are correct, and in the reverse, how many of the actual edges that we had in our original graph are like recovered, like predicted again. And then usually you report the F1 score because it nicely combines both of them. So another thing that we can do is looking at maybe some error metrics on the graphs, on the edges. And for that, we are considering the structural Hamming distance. So this is a like common also metric in general graphs. And what this tells you is to just look at every edge and again count up the numbers of like correctly and incorrectly predicted edges. So basically, we add an error of 1 if for some entry in our adjacency matrix, we have an edge that is predicted but not in the ground truth graph, or the other way around, if we have an edge in the ground truth graph but that is not in the predicted edges. So yeah, this is not a normalized quantity, and lower is better. So an SHD of 0 tells you have the correct causal graph. Yeah, and there's one like interesting thing or choice to make. So if you look at these two sums, what they tell you is that you iterate over all the edges in both directions. So we assume this is always like, these are always maybe not half edges, but like directed edges. So I to j is a different edge than j to I, which then basically means if your causal algorithm, discovery algorithm, detects an edge, but for some reason directs it in the wrong direction, then we count this error twice in this metric, right? Because for one, we say, well, this one edge I to j isn't there in our prediction. And on the opposite, the edge j to I is in our prediction, but not in the ground truth graph. So if you apply this metric, and it's in all the software packages, you usually have a parameter that lets you decide whether you want to like count these errors twice or not. And it really depends what you find more important, whether you just care about like the general graph structure, like the skeleton, then you maybe should just count it once. If you are about causal effects, then you might want to count it twice, but we will see another metric that does a better job at counting like causal stuff in graphs anyway. So yeah, then maybe let's look at some very simple causal chain. So we have these variables a to f, and we might wonder, okay, are all these edges equally important for answering causal queries? And so we might think of what will happen if we have some errors. So for example, we flip the edge a to b, and think of which of the independencies or dependencies that we had earlier might be violated or no longer be intact, and for which part of the graph all of this might still hold. So if we think of causal queries that are in this range E given do B, that is still intact. So basically all the causal queries like in this part of the graph are still intact, and only if we involve A for some reason, then independency statements might fail or switch. So again, we do the same thing for another edge, and now we direct C to D in another direction. And now we have a much stronger effect on our causal inferences, right? Because now basically these variables split up into two groups. If we change A, or at least if we change B, it no longer propagates all the way through F, but it stops at C already. So like if we are doing inferences in this graph where we like wrongfully discovered this edge, then we will get a lot more errors or wrong estimates when using this graph. And the question is now, how can we like formalize this or like, yeah, quantify this effect of edges? And this is what the structural intervention distance does. It basically looks at all the variable pairs in a graph or in the set of variables and considers, okay, if I have or had the query y conditioned on duo x, would I still get the correct prediction under parent adjustment? So basically it somehow measures how many of these queries I would get wrong if I like had errors in my graph. And some modifications in the graph, for example, edge additions, might not have an impact on the SID, which basically means for some of these queries, if I add edges, then this quantity would still be correct, because maybe I'm not introducing new confounders or something. So for some of these queries, I might have a different graph or a bigger graph, but my queries would still be correct. So the SID can still be 0 in some cases, even though the graphs differ a bit. But since we are talking about causal inference, we might also not care about these cases. Like, as long as these inferences are correct, we are fine. Yes. And on the other way, on the other side, depending on where we flip an edge in the graph, we can get a lot of these queries which are wrongfully predicted, or only a few of them. So this metric or this distance captures that. Yeah, something on complexity. Of course, we need to iterate over all the pairs. Then we need to search, like look for all the adjustment sets and check whether these queries still hold in both graphs. I just will leave it here. Yeah, so it's roughly on the order of p to the fourth with the log term and so on, but it's quite hard to compute, especially if you go beyond like 10 or 20 variables. If your graph is like moderately dense, it will take a long time to compute that. So this is a nice thing because we count all these causal queries and errors, but keep in mind that for larger graphs, this might not be applicable. Okay, then quick reminder on adjustment sets, right? So adjustment sets are, in plain words, the things that if we condition on them, they make our causal queries unbiased because they block all the paths between x and y, or at least all the non-causal paths. Yeah, I think we have seen examples. There are minimal adjustment sets. For example, here for y do x, the smallest one is p, and we can never condition on w because that introduces a bias. Yeah, let's keep with that. And basically, the interesting part is that specifically the parent set of a variable is always a valid adjustment set. Basically, if you think back to vector adjustment, what it did was to cut all the vector paths, which are specifically blocked if we condition on all the parents. And then, as I said, like doing this in code then is a bit more intricate and complex. But basically what this boils down to, and there are two different definitions which are equivalent, but I find this more like easy to understand. It really counts the number of incorrectly predicted adjustment sets. So this is why we, like before, said, okay, it looks at all the causal queries, and then it does not compute, like it does not every time apply the do calculus or whatever is going on, but it looks at all these pairs of variables and looks, okay, what in the ground truth graph are the parents in my yeah, for this one variable, and are they still present, or is this still the case in the predicted graph? Yeah, so basically it compares these two sets and then checks whether these sets in both graphs are the valid adjustment sets. Yeah. Just some properties of this SID. Basically, what we would expect, at least if the graphs are equal, the SID is 0. It is non-symmetric. Basically, so if we flip G and H, we can get different results. And in particular, if G is a subgraph of H, so that means we have more edges in H than in G, then the SID is also 0. So this might be important, or like if we give you two graphs and you see, okay, one of them just has some edges added, then you already know, okay, the distance will be 0. And the main thing is, so at the moment we are looking at, or we were looking at completely directed DAGs, but usually what you recover are CP DAGs. So basically what you can do is, in a smart way, iterate over all the DAGs that are entailed by this CP DAG. And I won't go into this. It's, I'm not sure if it's exponential, I think it is. But yeah, like you can iterate over all the DAGs and check all the independency statements. It's even worse in terms of runtime, but at least you can compare your graphs recovered by a causal discovery algorithm from observational data to the true graph if you have it. Okay, so some examples which are basically taken from the paper, which is quite insightful if you want to have a look at it. Basically, we have the true graph. We have graphs H1 and H2. And yeah, here we add this one edge from Y1 to Y2. And here we invert this edge from X1 to X2. Yeah. The SHD in both cases can be 1, or in one of them it's 2 because we count edge reversals twice. But like looking at this like very simple edge counting metric, we would say, okay, I mean, we made some mistakes, they are almost equal, maybe. So it's not too bad. The thing is, if we now look at the SID, which means, would we like to have H1 or H2 as a graph for predicting our like causal queries, doing causal inference or whatever? The SID tells us we would definitely prefer this graph, H1, because yeah, it basically added an edge, but all our causal queries will be the same, will be correct and unbiased if we recover this graph, and the true graph would be the G1. And here for H2, we see this single edge flip now introduces errors in 8 different queries, which basically is like, because here all the parent structures now changed, a lot of conditional independencies and whatever like got invalidated. And yeah, we get a lot of errors and make a lot of mistakes if we use this graph. So yeah, maybe as a yeah, concluding statement or whatever on this thing. So SHD and recall accuracy are nice, especially for larger graphs. I mean, they can give you a rough estimate on like how good or bad your prediction is. They are quite fast to compute. If you have smaller graphs and you care about not only the structure, but really what you want to do with the graph afterwards, if you want to use it for prediction, then you want to try and compare your new algorithm on a test set or whatever with SID, because it gives you much better estimates on how right or wrong you will be in your final causal queries. Okay, so we have that, and then there is some topic which came out quite recently, so 2021, where some people discovered that some data that we have might have some like biases or properties that some of the algorithms use, maybe sometimes implicitly or without knowing, but which is or might be important to consider. So particularly, we talked about additive noise models before, which are basically models where all the structural equations are a weighted sum of the parents plus some noise. And if you are not careful with like if you're generating data for benchmarking or something, if you're not careful with that, the variance of variables or of the variable values will increase the further down or the deeper a variable is in the graph. So assume all variables in the beginning have standard variance, all our noise values, for example. And then with more and more depth, we recombine all of these, and the variance, because we weight them and we add more and more noise, the variance will increase. And what Reisach and et al. Did was to leverage this property, and they call it var sortability, which basically means, okay, I look at all the correlations. I, again, like in the PC algorithm, recover my skeleton. But after that, what I do is I don't do meek rules or V structures, or maybe I want to do that, but I just go and look for every edge at the two variables and direct it in the direction of the variable with the larger variance. So we are somehow leveraging this implicit bias. And basically what I showed is that some of the algorithms, for example, FGS, Lingam PC that you saw before, they are relatively robust to that because they usually look at some properties of the noise terms. But some others, especially a lot of score-based algorithms, for example, node tiers, which was before that like really good in benchmarks, right? It performed even better than like all the classical algorithms. It suddenly drops a lot in accuracy or in also SID. So basically what this means is that it has some implicit bias that leverages this property. And that, for example, could be that by the way how it selects edges, it chooses the right variable order, right? We talked about this in the exercise about if we have a like total ordering of variables, we can always recover our true causal graph from or direct everything correctly given a skeleton. And this variance property might implicitly give us this total ordering. Of course, there are some, there are some details to that, but like in general, it works quite well. So basically, this is their approach, sort and regress, where they really do this ordering of variances, and you see as well it performs really better than all the classical algorithms. And once we renormalize the variable variances to 1, then it drops in performance. Yeah. So this is a bit about, okay, how do I benchmark my algorithms if I come up with a new one? But it also is an interesting insight in the other direction. So if I know my data is var sortable, then I can leverage this fact, maybe as a heuristic or whatever, to direct some of the edges, or at least direct them with higher probability or be more certain about them. So this might happen if you have, for example, some, I don't know, production lines, or I think also there is a river data set which is var sortable. So if you know there is really this linear additive things like rivers flowing into each other and so on, they might like feature this property, and there it's a valid thing to also use this information or this knowledge to improve our discovery algorithm. Yeah. So then just a quick remark on that. We need to adjust our benchmarks a bit. We need to to normalize the variances in our data. Unfortunately, that's not enough. Still, you can find a total ordering by looking at the coefficient of determination, which basically tells us, okay, how much do my parents, the variance of my parents, how much does the values of my parents tell me about the value of my variable? So because I have all the parents, which is some weighted sum, plus my noise term. If I would look at this, then we again get a causal order. And the problem, of course, is, yeah, that's nice, but if we're doing causal discovery, we don't know which of these variables are the parents, because that's the task we are trying to figure out. But still, we can just go and look at the undirected graph at the skeleton and just take as a proxy all the variables which are related. So there might also be some child variables in there, but like in a hand-wavy way, all of that like kind of averages out, and we still get an ordering which helps us to figure out the causal order. So just to be aware of that, like just renormalizing variables or variable variances isn't enough. Yeah. And in general, leverage all the knowledge you have about your data, because these algorithms are very brittle, and if you know of these kind of biases, then use them. So basically, before, in the previous lecture, we looked at causal identification with deduce calculus. And the thing is, what do we do if we have a CP-DAG, right? We have some undirected edges, so maybe we don't know the causal direction, and that might be a problem, because for applying the deduce calculus, we need to know about the direction of all the edges, most of them at least. So what we can do is basically we just iterate over all the DAGs that are in a CP-DAG and just compute our causal effects for all of them, right? And then just take the maximum and minimum value that we observe to get a bound. So the best and worst possible causal effect in a sense. Yeah. So the most naive approach is we look at our CP-DAG, look at all the undirected edges, and then we just direct in every possible combination. So first we start out directing them all in one direction, then we flip one edge, then we flip two edges, and so on, and iterate over all of them. The thing is, you need to be a bit careful about this, because if you remember how we constructed these CP-DAGs, you will see that if we observe such a structure, we had three possibilities, but the problem was that all these V structures we already had directed. So that means this structure can never be resolved into a V structure under all the conditions we discussed for instance. So what this means is, even though we might sample all of these graphs, we need to reject this one and only can have these chains in there. And then again, due to similar rules and so on, like acyclicity, right? If we know if we have a graph where one edge is undirected and directing this edge would form a cycle in one direction, we would have directed it in the other direction in the graph. But here it could be that like only a combination, like maybe only this one or this direction would form a cycle, then it might be that we can't conclude which of these cases we would choose. But still, if we would direct A to B to C, we again would form a cycle, so we need to reject all the graphs that would have a cycle in them. Yeah. So anyway, this naive approach is nice for simple graphs if you just want to write a quick test or whatever. But it's exponential because we need to iterate over all the edges, then do all the testing and reject some of the graphs. Then there is a causal order iteration, which is in factorial time. But the thing there is, depending on how many edges you have directed or not, it can be faster. Like, don't ask me on the exact details. But the nice thing is, like, rather recently, 2 years ago, there is a new algorithm. I don't have like a total runtime now, but basically what it tells me is that if I start with some DAG, I can have an algorithm which gets me the next DAG so that I can iterate all of them in the time n plus m, which is number of nodes plus number of edges. So this is currently the state of the art. And if you assume that, like, usually you don't have like a lot of these undirected edges, or you might have some of them, but they might be like connected in a way that we need to reject a lot of these graphs. This approach is quite nice because it basically upper bounds our search time for the next DAG. And given that we only have a handful of those, it's quite fast. Yeah. So again, as I said, we compute or look at all these graphs. We compute all the causal effects in every of those DAGs we get, and then just take the minimum and maximum. Yeah, it should be the other way around, but whatever. So you get the lower bound by taking the minimum. You get an upper bound by taking the maximum, and then at least you can make some assumption. So let's say you have a medical treatment. And so it's really easy. If the effects are always like positive minimum and maximum bound, then the medication always helps or harms, depending on how you phrased your query. If the bounds include 0, then it might help or harm or have no effect. Or if it's like goes in the positive and negative domain, you can't make any assertion about that. And don't be like misled with this kind of thing. So this is not like a bound or some probabilistic thing where you say, oh yes, sometimes the effect might be positive and sometimes it might be 0. No, like these bounds are what could be, but we assume there is one underlying true causal graph. Like one of those DAGs that we iterate over is the true one. We just don't know which one. Of course, you can make some assumptions about, like, maybe there's a higher probability if I have 100 DAGs and only one of them has shown no effect, all the others are positive, then you might say, okay, or with a higher likelihood has a positive effect, but we might be unlucky and still have the case where this one graph that has no effect is actually the true one. So we cannot like average or do whatever with these things, right? Okay, so before we looked at scenarios where we had uncertainties or difficulties identifying the true causal graph. And maybe we are certain about the causal graph, but we are uncertain about the mechanisms themselves. So a common common or sometimes used scenario is that of partial compliance. Basically, what this means is, okay, we asked some experts, they have conducted a study, and we have some treatment assigned. The patients then receive the treatment, and we observe the response. So it's very simplified. And there are a lot of latent factors, like, I don't know, the genes, socioeconomic background, I don't know, whatever beliefs, what they read on the news, or what their mood was at the day they should take the treatment. Everything goes in there, and we assume that these latent factors basically can affect whether they really took the treatment, and also whether the medication, for example, was working or was effective. Particularly, we assume also that the treatment assignment is independent of these latent factors. So basically, we are doing, for example, a randomized control study where we just randomly assign treatments to patients. And now I already hinted at this a bit. We might be a bit overwhelmed what to do with these latent factors, because we don't know them, we can't measure them, and we need to make some assumptions. And the most simple assumption we can make is that these variables are kind of binary. Yeah, so we say, okay, treatment assigned, yes or no, treatment received, yes or no, and observed response in terms of, okay, did it help or not, also a binary variable. And then for these latent factors, we have like 4 different cases that can happen. And particularly for the treatment received, it's these 4 on the left. So it's compliers that actually do what their doctors tell them. They just take the treatment if assigned and don't if not. Then we have always takers and never takers. So they don't care about their assignment. They just always take the treatment or not. And we have defiers, which for some reason like do the exact opposite of what the doctors tell them. So these are basically all the ways a patient could respond to treatment in this scenario. And it basically discretizes our latent space. Then we have the exact same thing for the observed response. So we could say, okay, it either helped or hurt. So yeah, depending on some of the latent factors, the medication had an effect or had no effect. And then we have these patients where, yeah, we have no effect. Oh no, the hurt case is it made the situation worse. But we can also have patients where it doesn't matter what whether we did the treatment or not. They would have always recovered, or they would have never recovered. And the question now is, okay, in this graph with all this uncertainty, what is actually the effect of my medication? So assume I do take the treatment, take the medication. What is the average causal effect or average treatment effect of like taking it versus not taking it? Yeah, in our expectation that the medication helps, or that we have a positive outcome, that the patient recovered. So the thing is, it's a bit tricky to apply do calculus in the like standard case, but what we can do is we can, again, like we discussed before, iterate all the possible cases, and I will just give a rough sketch, and just to show you that it can be done. And in the paper cited here, you can also read like the exact details. But basically what we can do is, first of all, we look at all these combinations that we have for v and y, and just create a list of all of these possible combinations, so 16 of them. And we know whatever sample we observe, it needs to correspond or have a latent class of any of those 16 things. Basically, what this then means is that we have a probability distribution over this, and it tells us, in the end, they all need to sum to 1. And for some observations that we have, we know that some of these latent factors or these combinations, these settings can apply and some cannot apply. For example, if we observe that we assigned the treatment, the patient took the treatment, and the patient recovered, then we could, for example, have the scenario where the patient complied or had this tendency to comply with the treatment, and that the patient might, because of the treatment, would have recovered. An alternative consistent setting for this observation would also be that, yeah, sure, we assigned the treatment, but the patient would have taken the treatment anyway, whether or not we would have assigned it. And independent of whether or not the patient would have taken the treatment, he would have always recovered. So this is also a valid setting or value for our latent variable. And equally, some of these settings are cannot be. So we know if we observe the patient has taken the treatment, we know it cannot this never take a latent factor or value. So basically, what we can do, we get some sort of constraint. So in the paper, they assign some shorthand notation to it. And basically, we have constraints which bound the observations to the probability distributions of this latent space. Yeah. Exactly. And the idea is that we will then add more and more of these constraints and get a restricted space where we do apply linear programming, which basically finds us the minimum and maximum bounds or effects in this restricted space. But for that, maybe look at other lectures, how to do it exactly. I think it's enough if we now here don't go into the details and just say, okay, there are packages and algorithms for that. Yeah. So as I said before, the probabilities somehow need to match the data, like our observations. If we observe, for example, like just theoretically, that there was always the treatment taken, then we know the probability for the never takers must be 0, right? Like that's bound because it can never be, because we don't observe any data that complies with this latent factor. Again, because these latent factors are form a probability distribution on their own, they must sum to 1. And then we have this thing. So this is assignment of P given our observational data. And here is then a list of 16, no, because it's constrained, I think it's only 15. Yeah, of 16 of these equations, which basically iterate all these consistent settings, right? So if a patient is not assigned a treatment, does not take the treatment, and does not recover, then we have 4 different terms of these latent factors that could explain this this observation, this sample. And that we do for all possible combinations. So if we don't assign a treatment, but we observe the patient taking the treatment, but then not recovering it, this is then captured in the second one, and so on. And yeah, basically this is the setup that we then give to our solver, and basically ground it in the observational data and infer the probabilities of these latent classes, or the bounds of the probabilities for these latent classes. And then again, once we have these bounds, we can recombine them, because if you look at that, right, that's just vector adjustment, and we just can assume now some of the values, or we know the upper and lower bounds of values in U, and so we can average that out. So really, this is a rough sketch. The paper is much more detailed, and I think it would need a whole lecture probably. But yeah, just to let you know that you can do it, that in the case where you can discretize and iterate over all these latent states, you have a chance to infer these bounds via linear programming, and they in the end boil it down a bit more. But yeah, so this is the often used case in these settings where we aren't really sure what the patients are doing, what the true underlying mechanisms are. Yeah, and this is quite nice in these simple settings. Just be aware that if we have more and more of these latent factors and more variables that are affected by these latent factors, here we have these Cartesian products, right? So that means the number of constraints and the number of equations we need to fulfill blows up exponentially. So even if we have like 10 variables all affected by this latent factor, this might already become a problem, because we need to solve this whole system. There are efficient solvers, but yeah, be aware that if you can make some assumptions which variables are affected by U and which not, or if you maybe can split some of the U's into separate variables, then do that, because it makes the problem easier. Okay. And then finally, I just want to do a very brief look again at continuous stack constraints. Florian showed it very briefly in the last lecture with no tiers, but I just would like to show you some of the reasoning behind it in case you need it or want to apply it in some other scenario. As I said, this no tiers, it basically algorithm basically minimizes some score according to the data. And because we are in a causal setting, although they are very careful with calling it causal, we apply a DAG constraint to avoid cycles and so on. And this constraint is, at least I find it quite interesting. The thing is to apply standard optimizers and so on. What we would like to have is a smooth and differentiable function. And this might be a bit tricky to achieve, because if we think of like acyclicity constraints, what we have done so far is somehow like explicitly go through the graph and search for cycles, right? Like iterate all the nodes and whatever. And this might, like, by default, this is not differentiable. So we need something smart to make it work. So maybe like in the introductory computer science courses, you have heard some properties about graphs and adjacency matrices. And one interesting property of adjacency matrices, of weighted adjacency matrices, is that if we take the kth power of a matrix, the entries contain the sums of the weights along path from I to j of length k. So basically what this means, if we look at the w to the power of 1, we get all paths of length 1, right, which are just the direct edges. And in these entries of our adjacency matrix, we see the weight. So if we apply, or if we multiply our matrix with itself, we get in all of the entries the sum of all the paths of length 2, like all the weights that go into it, and so on. So what we can now do is, well, if this power of a matrix tells us that we get all the paths from one variable onto the other, why don't we look at the diagonal elements, which I, for some reason, wrote as ij, but is like this is double I. So it's the diagonal, which then tells us the self cycles, right? So if the diagonal is 0, it means at least for some power k, there are no paths of this length. And this is, or might be interesting, because computing this is somehow differentiable, and we just can look at the diagonal, basically look at the trace, and check whether it's 0. Just a small disclaimer, we will fix this in a bit. The trace sums up all the diagonal elements. If we have negative values, then things might cancel out, but we will, okay, I said here, we can just square all the weights, because we are not so much interested in the exact weight, but just whether it's 0. So we don't care if we have a positive or negative weight. If there is some path, no matter its weight, we have a problem, kind of. So what we would like to have is really this matrix, or this trace, which is 0, which is only fulfilled if all the trace or the diagonal entries are 0. So the thing is, again, okay, it's cool that we can look at individual powers and check this property, but it might be a bit expensive to check for all of these powers. So I've written here until like infinite exponential, but of course, I mean, we know a path can at maximum go through every variable or every node once. So there is a bound, but still we might want to avoid like computing all these exponential, especially for larger graphs. That this might get expensive and maybe also be a bit unstable numerically. So the idea is, and don't ask me how you get to this result, but if you consider the Taylor series of the exponential function, it expands something like this. And the same thing we can do to matrices. Or instead of having real numbers there, we can plug in matrices, which then gives us this formula. And this is a matrix exponential. It's super helpful for all kinds of graph-related things. for proving, I don't know whatever properties. But the interesting observation here is that by computing this, we get all of these powers of the matrix in this series. So of course it's somehow weighted and whatever, but we just sum up all the matrices. So what we could expect is that if for all of these matrices the trace is zero, like the diagonals are zero, also for the sum matrix the diagonal will be zero. So there's one small catch. Basically, we apply the trace again. We just apply it to the exponential directly. We can like pull it in there. And here we expect all of them to be zero. So they cancel out, or like they vanish. And here we have this one, or this identity matrix. And basically the trace here, right, it's all ones on the diagonal. So this one term evaluates to the number of nodes, which basically gives us the result. This first term is the number of nodes. All the rest evaluates to zero. So we get this equality. The trace of the matrix exponential minus d should be zero. And this is in the form of the constraint that we defined before. Because all of this is differentiable, we can plug it in. It has a quite easy gradient also. Yeah, so again, to avoid negative coefficients canceling out terms, we just take the Hadamard product, which like pointwise, in this case, squares all the entries. So we get this expression. And this is then basically our Dagnus constraint. The thing is, okay, if we were to compute this matrix exponential via this Taylor series, we wouldn't have gained anything, right? Because then again, we would need to compute all of the terms, again, compute all of the matrix powers. But the nice thing is, this exponential can be computed in different ways. There is an approach called scaling and squaring. Harder approximations you don't need to care about, but it's quite robust and in the complexity of number of variables cubed. So instead, we derived or justified it to use this exponential via the Taylor series, but then we use a different way of computing this. That's a good question. So there are actually follow-up works of this. And of course, I think the problem here is because you have all these scaling and whatever, it also is numerically not really stable to do it via the Taylor series. I mean, you could compute the individual terms, but still, like practically, even if it's in the same complexity class, it takes way longer in practice. So this is numerically stable and faster. So yeah, and then there are optimizations which do other weird tricks and things like looking directly at the traces and so on. But this was the first method, and I really found this connection basically between the matrix exponentials and looking at the trace as self-cycles quite insightful if you encounter it in like other settings. Yeah. Yeah, as I said, so this M method computes matrix exponentials in the SciPy package, for example, and they're using some like, I'm also not really sure, I think it's some numerical whatever iterative approaches to approximate this exponential, but it's not, I mean, it converges to the same value, but it doesn't compute it via this sum, right? It does something else. Yes. And then I'm not sure if there are any questions left. So this is basically the last course on core causality. And next time we will start with causal abstractions and a bit of the more fun stuff. Okay, then if there are no further questions, thank you and see you next week.